So in the following, we want to understand how many possible join trees we can have. Reconsider that the join operator is a binary operator, so these join trees are binary trees. And if we have n relations, the join tree has to have n leaf nodes. The number of binary trees with n leaves is given by the Catalan number of order n-1, which is defined here, what that means. It's not so important to understand why you can write it in closed form like this, but it's important to notice how fastly this is growing with n. That means if we have n, number of relations, quite large, we have an immense number of trees to consider. This are only the structurally different trees. So if you have like n equals to, let's say, 4, and then the Catalan number of n-1, so in this case 3, will give you the number of structurally different binary trees with 4 leaves. Yeah, for instance, this is 1, then we have another one, and so on. Right? And you could enumerate all of it. You can try now to draw all of them. And if you're trying this for 4 leaves or 5 leaves, 6 leaves, and so on, you see that this is really exploding the number. So it's very important to reflect this, because this is also a major influence on the performance or the problem of looking at the best possible solution because of this large number of binary trees. Let's assume the case of allowing cross product. So every relation is joinable with every other relation. And we have n relations in total. How many left deep trees can we construct? Well, left deep trees always look like this. Right? There's only one way they can look like, exactly like this. Of course, they're getting larger or smaller depending on n, but they always look the same. So there's only one possible structure of this left deep tree with n leaves. N leaves because we have n relations, right? And now, how many possibilities we have in order to assign these n relations to the leaves? Well, n factorial, right? So here we have choice of n, n-1, and so on, right? Very simple. So we have one possible structure and n factorial many possible assignments of the relations to the leaves. So in total we have n factorial, many left deep trees. It's important here to consider that we allow cross products, because otherwise it's not perhaps possible to join relation 7 with relation 8, because there's no edge in the query graph, right? And then if we cannot join R7 with R8, then in the assignments of the relations to the leaves, this would not be possible, right? But since we allow cross products, we have the full variety of n factorial many of these assignments. Okay. For right deep, it's the same, because there's only one way right deep trees look like. Well, right deep, right? And we have again n leaves, so we have again n factorial many ways to assign the relations to the leaves. And for zigzag, it's getting a little bit more complicated. Zigzag is also linear tree, right, like the other two, with the difference that the input relation to the join operator is not fixed to be a relation on the left or right side, depending on the left or the right deep trees. In zigzag, it has to be at least one input, has to be like a relation. So what that means for the structure is that we can swap here, we can swap there, we can swap there, and so on. We don't have to swap, but we can swap. So we have in total n-2 places in the structure of this left deep tree I have illustrated here. We have n-2 places where we can swap the inputs to make zigzag trees out of this left deep tree. Since we have n-2 ways where we can swap, we have 2 to the n-2 alternatives. But every time we can decide, do we swap or not, for each of these n-2 places. So we have 2 to the n minus 2 different shapes, or structures of zigzag trees. And now we have the 2 to the n minus 2 structures, and we're multiplying this by the number of possible assignments of the n relations to the leaves, which is again n factorial. So in total we have n factorial times 2 to the n minus 2 possible zigzag trees. For bushy trees, now we can use what we have seen earlier with the Catalan numbers. So we have Catalan number of the order n minus 1 possible structurally different trees. And again, these trees have n leaves because we have n relations. And since all of the relations are joinable because we have cross products, again, we have n factorial many different assignments of the relations to the leaves. So n factorial times the number of structurally different trees is this one, and this can be rewritten to this equation, right? To this fraction. So the idea again, look at all possible combinations possible, assigning the relations to the leaves, times the number of possibilities to create a tree given this restriction of left deep or right deep or zigzag, or having no restriction at all for the bushy one. Right? The number of trees grows exponentially, and even more if you're allowing more flexibility in the tree structure. Right? And bushy, of course, grows fastest. Now, fortunately, we can reduce the problem if we have the case of not allowing cross products. Because then if we have a chain query, so R1 can be joined with R2, and this can be joined with R3 and so on, then we do not have this n factorial many assignments of the relations to the leaves. So we don't have cross products. And if we then also say we only restrict ourselves to left deep trees, as some database systems do, to reduce the search space, then in the end we can derive a more concrete formula for the number of possible left deep join trees for the special case of chain queries. Right? We will not go through the derivation. In the end, you're getting some complicated looking equation out. But you can write this down as a closed form, if you're doing the derivations right, as 2 to the n minus 1. The number of possible join trees for n relations, left deep join trees, n relations without cross products. So again, it's only one possible structure. We're having left deep, and this is the number of possible assignments adhering to the fact that you cannot join all the relations with, like, every relation with another relation. This has to follow the chain query graph. So in the end, you don't have n factorial, but 2 to the n minus 1, which is better, right? And if you consider zigzag trees, again, you can multiply with 2 to the n minus 2 because of the swapping possibilities in each of these stages I have just marked. But as you can imagine, 2 to the n, even minus 1, doesn't matter really much. It's still growing quite fast, if n is growing. You can also specify the number of possible trees if you consider bushy trees. Again, we consider now the case of having a chain, so no cross products. And we have again the same chain. So you have to make sure that when you're creating a bushy tree, which can look like this, of course it can also be linear, right? This is important. But here, when we want to join two relations, let's say R1 and R7, we have to make sure we can only join these two here in the subtree if they are like neighboring in the chain. Otherwise we cannot join them because we don't have cross products. So in the end we can derive that we have 2 to the n minus 1 possible combinations for the correct assignment of relations to the leaves according to the chain query graph, right? Times Catalan number of the order n-1 for the structures, right? Let's consider star queries. So we have like this shape looks like this. The query graph looks like this. So we have relations R2, R3, R4, and so on. And in the middle here we have R1. This is our assumption here, right, for the illustration purpose. Now, how many possible trees can you build here? The interesting observation is that in the first join that you're doing, there has to be R1. Why do we have to have R1 in the first join in any tree we can have? Well, if we have, let's say, looking at depth deep trees, which again always looks like that, right? Easy to draw. How do we start? Well, we cannot start joining R2 with R4 or whatever, right? Because they don't have an edge in the query graph. So we cannot join R2 with R7 either and R2 with R5. We have to start something, doesn't matter what it is, because they're all joinable with R1, but R1 has to be there. Yeah. So for the first join we're doing, we have only two possibilities, depending on R1 being the left input or the right input. For the other places, we again have a free choice, like we would have cross products, because once R1 is present in the join, every other relation can be joined because R1 is connected to all of the others in the query graph. Right? So overall, for left deep trees, we have 2 times n-1 factorial. 2 comes in here because of the 2 possibilities of where R1 is placed. And for the other places, let's say we have R1 as the second input, so the right input, then we have n-1 here still to fill. And they can be arbitrarily placed because they're all joinable with R1. So we have 2 to the n-1, or 2 times, parenthesis opening, n-1 factorial, right? For zigzag, we have the same situation as before. We can generalize the left deep tree number of possible trees by multiplying with 2 to the n-2 because of the possibilities to swap the inputs. And now, this is something to remember, like of course everything needs to be remembered, but like this is like something we often ask. So how many bushy trees do you have? You cannot have any. You cannot have any bushy tree because how do you start something? I mean, so now I have to be precise. So how many bushy trees do we have which are not linear trees? To be precise, right? Because bushy trees means also we can have like a left deep tree or a zigzag tree. But now we mean here how many bushy trees you have or you can create which are not linear trees. And the answer is not any. Not possible to do that, because how would you start creating something like this? Yeah. So if R1 is here, okay, you can put anything you want here, R5 let's say. But how do you join this? You cannot join it because R1 has to be present. But if R1 is not present, there's no other pair of relations you can take to join, because look, there's no edges here, right? That's an interesting observation for the case of star queries without cross products. For clique queries, so where the query graph is a clique, every relation can be joined with every relation. So it's the same as considering that you're allowing cross products. Okay, let's put in some numbers to see how fast this number of trees is growing with n. Here we have chain queries, so where R1 is joinable with R2 and then with R3 and so on. and here we have star queries. Let's look at the chain queries first. So here we see left deep trees, and right deep trees of course has the same number. So here it's growing 2 to the n-1. Again, no cross products and chain queries, right? So it's very restrictive. So it's going for n is 2. We have 2 possibilities to do that. We're just like flipping the inputs. It's like a very simple case. And then we're going to 3, 4, 5, 6, and so on. You see already for 6 we have 32 possible left deep trees, which means basically 32 assignments of possible adhering to the chain query, the 32 assignments of relations to the leaves of this left deep tree. Okay, that's already more, right, than 2. And depending on how costly it is to compute like a cost model over these trees, if you want to enumerate all of the 32 for 6 relations, then you have to spend also some milliseconds or nanoseconds ideally to for the cost model, and then you pick the best one out of the 32, and then hopefully this is a good plan. If you say that you want to have more flexibility, because left deep might not always be the best one, well, in general it is not always the best one, right? So, and you have cases in practice where left deep trees are not good, and you want to allow also zigzag trees. Look what's happening then. You have to consider already 512 different zigzag trees, right? So linear trees. Of course, these 512 include these 32, because zigzag is a superset of left deep. And then you might say, let's go for the real answers, and we look at also bushy trees, which include zigzag and left deep. We have like 1,344 possible query plans to consider, or like join plans to consider. And you can imagine that this gets costly, even if the cost model can be applied quickly. So then you have to make sure that the query optimization still pays off and it's not too much time wasted to look for these the optimal plan, allowing maximum flexibility. Perhaps these would also do in practice, right? That's always a trade-off. Some database systems, they restrict themselves to left deep trees, so to avoid this explosion like for the bushy trees. Then if you go to star queries and look at left deep trees, just look at numbers. They're also growing, of course. There's like more flexibility once you started with the first inner relation, and the other ones can be arbitrarily placed. And for zigzag or bushy, bushy does not exist if you don't have cross products for star queries, but it's the same than zigzag. Bushy, not linear, does not exist, to be precise, right? So it's zigzag in this case. And you see how crazy these numbers go up. If you allow cross products, that means that the query graph shape does not matter, because you can join everything with everything, just like in the clique query graph. Well, look at the numbers. Now you have not 32 for 6 relations, but 720 for left deep. It's factorial, right? We know how fast factorial is growing. And if you go for zigzag, well, it's a factor of 2 to the n-2 more. And then here for bushy trees, we have 30,240 possible join plans to consider. If you want to look at all of them and see what is the cheapest one. And it's kind of clear, the larger the search space is, if you're allowing cross products, your search space gets much larger. And if you're allowing bushy trees, so arbitrary trees, well, it's also more flexibility than restricting yourself to left deep or to zigzag trees. And if you're going for the full number, so cross products and bushy trees, if you're looking at all of the trees, there will be the cheapest one among these, right? But the problem is that you have an immense number of combinations to consider. Right? So it's like a trade-off always between a huge search space and the guarantee to find the cheapest one, or having a little like a restriction on no cross products, for instance, or like the left deep trees, having less search space, and maybe you're missing the best plan. But it's often also said that it's not about finding the optimal one, it's about finding a good one, right? Because in the end, the difference between the good one and the optimal one might be marginal in practice, in particular also because all of these computations are based on statistics and independence assumption between different selectivities. So often, or in practice, it's often good enough to look for like a restricted case. So let's look at how we can find good or hopefully optimal join plans. The first algorithms we consider are greedy algorithms, so they cannot guarantee, of course, to find the optimal one, but depending on how clever you are designing these greedy algorithms, you can get good results. These greedy algorithms, there will be 3 of them. They're always getting more and more advanced, not really very fancy algorithms, but they're always trying to solve some problem that the previous greedy algorithm had. So they're getting fancier and fancier. Why do you do this? Why do you do greedy algorithms? Yeah, just what we said earlier. The search space of possible trees can be a huge number, very large, and the query optimization should not take a lot of time, so we have to come up with very quick algorithms. And these greedy algorithms are, well, greedy, so they're not promising to be exact, but they are, they're fast, right? So what we do in the following algorithms, we consider left deep trees. So it always looks like this, right? Left deep. And what the algorithms output is a sequence of relations. So basically we are sorting somehow these relations. And then the sequence that is produced will be just put in this order now to these leaves of our left deep tree. So the algorithm that you see now will not produce a tree, it will produce a sequence, but then we just go and put the sequence here, right? That's the idea. Okay, here's the first one, greedy 1, or greedy join ordering 1. It takes as input a set of relations and a weight function. For instance, cardinality. Weight function takes a relation and maps the relation to a real number in general. So, okay, let's look what the algorithm is doing. We start with an empty sequence. That's our output sequence in the end. And as long as our set of relations is not empty, we pick out of this set R the relation that has the smallest weight. So we iterate over all of these Ri or from R and take the one with the smallest weight. That's done in this line here. So argmin in contrast to min, so if it would be only min, probably you all know this, but let me just say that. So min would get the minimum weight, the number, and argmin would return the relation, so the argument that makes the minimum weight. Okay, so this is now m. Then we remove the relation we just picked from our set of relations and append it to our sequence. When we are done, we return the sequence. Then we take the sequence and put the sequence as the leaf nodes of our left deep tree. The problem is that if you're picking, let's say, R7 first, because of this here, the next ones, which is R without R7, the next ones to pick somehow intuitively should depend on the already done choice of R7. Because you want to pick the next one to be the one that has a very small join result with R7. That's the rough idea. But you cannot do that because the weight function does not take into consideration what you have already picked. It will just depend only on the relation itself. Now, so we have to come up with a better algorithm that is allowing the consideration of the already picked sequences for the next greedy choice. And this is exactly what greedy 2 is doing. So the second algorithm, it takes again the input as a set of relations, and then the weight function would take as a parameter the relation we want to investigate if we should pick it next, and a set of relations which corresponds to the already selected relations that the algorithm has produced. The algorithm looks very much the same. So we again have this argmin function which iterates over all the relations that are remaining in our set R, and then picks the one where this weight function is smallest. And look, the difference here, the second parameter, this is like the so far already selected relations in our like temporary output sequence S, right? So we would not only consider, let's say, the cardinality of Ri here, but we can look at, let's say, the selectivity of Ri regarding all the other relations in S. So the decision which relation to pick next can be based on much more information than only looking at the simple weight as in the greedy 1. And hopefully the greedy 2 will produce in general, or in, let's say in practice, better results than greedy 1. So now, is this the end? No, probably not. You guessed already, because I mentioned earlier we have 3 algorithms here for the greedy cases. Why are we not done? Well, the observation is that the first relation, of course, still needs to be picked based on, let's say, the size of the relation, because there's no other sequence from previous selected relations to consider, because the first one, when we want to pick it, S is empty, right? So depending if we, let's say, decide to pick R5 first, then no matter what the other decisions are, the first join will always involve R5. And perhaps this is also not the best thing to do. So the idea for the greedy 3 algorithm is to vary the starting relation to the first pick. Okay, here we go, greedy join ordering number 3. The same input, of course, because we have to still solve the same problem. Also a weight function, considering the relation that we want to see how good it is in terms of our weight and the previous selected ones. And now, what I just said, the idea was coming from greedy 2 to greedy 3 that we now vary the starting relation. And well, how do we do this? Well, here we have a for loop which allows every relation Ri to be for one run the starting relation. And this is pretty much the same as in the greedy 2. The only difference is we execute now the greedy selections of the sequence for a specific Ri to be the first one. And now we have, of course, multiple sequences where every Ri has a chance to be the starting one in the sequence. And from all of the sequences, we pick the best one regarding the weight, where we look at the last picked one and the sequence before, right? So we try out all of the starting relations, and then we starting the greedy picking again, like in greedy 2, and in the end we pick the sequence. We have multiple sequences, like how many relations we have, the many sequences we have to pick, and we pick the one where the weight of the last picked relation regarding the n-1 previous picks is smallest. And this is solving the problem that greedy 2 had. And greedy 2 solved this problem that greedy 1 had. So you see, with every step here we made an improvement.